In this lesson, we're going to look at the concept of a scatter plot, a line of best fit, correlation, and collinearity. So to start off, we have an example. It says Emily measured the depth of water in a bathtub at 2-minute intervals after the tap was turned on. The table shows her data. So why we're keeping track of Emily and the water in her bathtub, I don't really know. But anyways, here it is. So we're asked to make a scatter plot for the data. You can see that where we normally have our X values, we have the time in minutes, and where we have the Y values, we have depth in centimeters. Remember, time is our independent variable. That happens no matter what. And the depth of the water is the dependent variable. It depends on the time, how long the water has been running for. So when we look at our table of values, we see that the time is starting at 2 minutes as our first point, although we would have started at 0 time, and it goes up to 22. So when we go to put our values on the grid, we want to make sure that we're going to get from 0 all the way up to 22. And usually we want to go a bit beyond 22 in case we're going to make some estimations based on our line in our graph past that point. In the same way, our depth goes from 7 all the way up to 47. So we want to make sure that whatever we count by, we can get all the way up to at least beyond 47 a bit. So if you look at how many lines we have here, you can tell that we're not going to be able to count by ones to get all the way up to 47. Here you can see that we've labeled the axes. So at the bottom in time, we have counted by 2s, and we've labeled them every other one. So, or we're counting by 1s if you count all the lines. And then up the vertical axis for depth in centimeters, we're counting by 3s and we're labeling it every other one. So you can see that we'd go 0, 6, 12. So we couldn't count by 1s to get all the way up to our value of 47. So now that we have our scale written out, we want to start to plot some of the points. So at 2 minutes, the depth is 7 centimeters. At 4 minutes, 8 centimeters. At 6 minutes, 13 centimeters, and so on. So here you can see we've plotted all the points in our graph, and we also have the title, Depth of Water versus Time. Now question B asks us to describe the trend that we see in the data. Now even though these points aren't lining up exactly on a straight line, there definitely still is a trend or a pattern. You can see that as time is increasing, the depth is getting larger. So yes, we do have a pattern, we have a trend, and trend is just another word for pattern. So what we could say is, as time goes by, the depth of the water is increasing. Question C asks us, does the relationship appear to be linear? So again, just because the points aren't exactly in a straight line doesn't mean that it's not linear. We have a pattern that represents a line in the way that it's going, so it does seem to be a linear relationship. In question D, we're asked to use the graph to extrapolate or estimate the depth of the water at 28 minutes. So what that's asking us to do is to go beyond our data points when it says extrapolate. So we've got data points that go from here all the way to here. If we were to make estimates within these points, that's called interpolating because it's within our data points. We're going to be looking beyond. That's called extrapolating. So if we were to extrapolate or estimate the depth of the water at 28 minutes, we'd come over here to 28, and we're going to estimate, based on the pattern that we see, approximately where would we be. So again, this is all an approximation. It's not the most accurate, but we could say it would be at about 60 centimeters. Then the next part says line of best fit. That's a straight line that best represents the data on a scatter plot. This line may pass through some of the points, none of the points, or all of the points. So here are the rules for a line of best fit. You want your line to represent the pattern of the data that we see. So here you can see that as we go to the right, it's going up. So our line should be doing that, representing that. We want it to go through as many points as possible, with about half of them above if they don't fit on the line and about half below. If we have any points that are just way out there and aren't following the pattern, we ignore those. So those are called outliers. So let's draw our line of best fit. So here we've got a line. There are 5 points, 1, 2, 3, 4, 5, 6, 7 points below and 4 points above. So that's not as good as we could get. Now we've got 4 above and about 4 below. There, that's a pretty good line of best fit, which is approximating the pattern that we see. Now notice that the line of best fit is not going through the origin, 0, 0. Sometimes people think that the line of best fit has to go through the origin. It doesn't. Not every line has a y-intercept of 0, and here it doesn't. So we've got our line of best fit drawn, and then in E we're asked to determine the slope of the line of best fit. So in order to find the slope, we want to figure out the rise of the run. So you can pick 2 points on the line, not 2 of the red dots that aren't on the line, but points that are clearly on the line. So here I would say that one good point might be right about here at 5 and 12, and another good point might be over here at 11 and 24. So when we go to find the slope, slope equals rise over run, so we could just count the rise over the run, or we could take y2 minus y1 over x2 minus x1. If we do that, 24 minus 12 over 11 minus 5, that'll give us 12 over 6, which is 2. So our slope, m, equals 2. So what that tells us is we are going up 2 centimeters per minute. Next, we're asked to determine the y-intercept of the line of best fit. So if we wanted to do it algebraically, we would write y equals mx plus b. We'll replace m with the slope that we found, which is 2, and then we'll use a point from the line, not one of the red dots that isn't on the line, but one point that we're relatively confident of, and replace that for x and y. We used 5 and 12 as one of our points, so let's replace that. And we get the y-intercept is 2. So when we're asked to write the equation of the line, we can write y equals 2x plus 2, but of course we're actually talking about something in a context, so we're talking about the depth of the water and time. So we would write the depth of the water equals 2 times the time plus 2. Question H asks us to use the equation to predict the depth of the water after 47 minutes. So because we have our equation written with D for depth and T for time, that makes it easier for us to find our answer. We can write our equation D equals 2T plus 2, but instead of time, we can write 47 minutes in that spot. 2 times 47 plus 2 is going to give us D equals 96, and the measurement is in centimeters. So at 47 minutes, the depth will be 96 centimeters. Question I says use the equation to predict when the water will reach a depth of 73 centimeters. So again, we can use our equation, but now we have the depth. D is 73, so we'll write 73 equals 2t plus 2. We'll subtract 2 from each side to get 71 equals 2t, and then we can divide each side by 2 to get 35.5 minutes equals t. And again, remember, 0.5 minutes does not mean 5 seconds. It's 0.5 half of a minute, so that's 30 seconds. At the bottom of the page, we have some definitions. So first it says a scatter plot of the relationship between two variables shows a positive correlation when the trend is increasing towards the right. So what that means is if we have a graph and the trend is increasing, so it's going up as we move towards the right. So as we move towards the right, the points are going up. That's a positive correlation, just like a positive slope. A negative correlation happens when the trend is decreasing towards the right. So if we are going towards the right, but the data is going down, that's a negative correlation. And no correlation happens when there is no pattern either way. So the points are just randomly all over the place. We couldn't draw a line that would represent all of those dots because they're just everywhere. So that's no correlation. Then it says a correlation is strong if the points nearly follow a line or curve, very strong if the points follow a line or curve perfectly, or almost perfectly, and weak if the points are dispersed more widely but still show a recognizable trend. So these are just ways to describe how closely the points are sticking to a line. So very strong would be something like this. The points are, there's a bunch on the line maybe, and then they're pretty close to it. Strong might be over here where we'd see that it's definitely showing us a pattern. And weak would be something more over here where, again, we do see that we're increasing, but they're not as close to the line when we draw our line. Down below it says, the scatter plot is linear if the points lie along or close to a straight line. So all the examples we've been doing so far are linear. So here, this is a linear scatter plot. But we can have a nonlinear scatter plot when the points are close to a curve. So here we have an example of exponential growth where the points are going up and curving like this. That's nonlinear. Question 2 says, determine the line or curve of best fit for each of the following scatter plots and describe the relationship. If the relationship is linear, then determine the equation of the line of best fit. So here, if we were to look at this graph, you'll notice that the points are increasing as we go to the right. So we've got a positive correlation. If we were to draw a line of best fit, we'd have about half the points above, half below, with as many on the line as possible. And you'll notice that right here, we ignored the outlier. We didn't try and make our line come down and curve or do something weird. It seems to be a measurement of data that was just out of a regular range. So maybe we made an error, or it was some sort of anomaly. Also notice that we've got this squiggle line, which means we skipped counting. So we started at 0 and then we skipped some values. And this is just a bit of a typo. It should be 120 and 160 here. So when it says describe the relationship, we could say that this has a very strong positive correlation and there's an outlier at 15,45. To find the equation of this line, we would pick 2 points that are on the line. So maybe this point here and this point here. We'd find the slope, and then we could use y equals mx plus b, replace m with the new slope we found, and the x and y value with one of those 2 points to find the y-intercept, and we would have all that we need for the equation of the line. Question B says that we have a graph where it's showing us time traveled to school versus height. So we've got height in the bottom, and we've got time in minutes up the side. And if you look at the graph, you can see that the dots are all over the place, which makes sense because your height really will have no bearing on how long it takes you to get to school. They're not connected in any way, so there's no correlation. So that's what we would write, no correlation. So we wouldn't draw a line of best fit because there isn't a line that represents the data nicely. It's all over the place. I have no idea what kind of line you draw because you can't. So we don't draw an equation here, we just leave it. Then the last example says height versus time for the path of an arrow. So this one is not linear. You can see that we definitely have a pattern. As time goes on, the arrow is traveling up in the air, so the height is increasing, but then eventually gravity pulls it down and it comes back down. So we could draw a curve of best fit, but not a straight line of best fit. So it is a strong relationship. It's very strong. It's following a really nice pattern, but it's a non-linear correlation. And there is an equation, but we don't look at curves and equations in grade 9, so we'll just leave that for now.